first of all, thank you guys for coming here, and thank you for taking the time to come here, actually. So, my project is Denial of Service. My name is Cruz. I'm a computer engineering major at SPCC. This summer, I'm working at the computer science department under the faculty advisors, Richard Kimmer, Christopher Cruz, and Giovanni Vigna. This summer, I'm also working with a PhD grad, which is a professor who is a professor now, Adam Dupé, and we are working on this popular hacking type called Denial of Service. There's a lot of interest in this Denial of Service, as you can see. These are our funding sources. But what is Denial of Service? Denial of Service is basically rendering a system unusable, unable to provide services to the user. Right? So if you go ahead and smash a computer, that's technically denial of service because the computer can no longer provide services to the user. Right? This attack has gained notice recently because it's been noticed that it can actually inflict major damages on businesses. As this is an example of one. In 2013, Mt. Gox, which was the largest Bitcoin exchange, crashed because of this attack. And a lot of people who are invested in Bitcoin lost their money because of this. So before this attack was simply being used to pull pranks on websites. However, now it's actually being used to manipulate stock exchanges. So we can all agree that that's pretty bad, right? I've already mentioned one type of denial of service, which is like smashing a computer, disconnecting the wire, unplugging it. All those things, right? That's basically the main definition of denial of service. Another one is hardware denial of service. As you may know, internet consists of communications between computers. But in between those communications, there are electronics. And so what hackers do is they attack those electronics in between, rendering those computers unable to communicate and unable to receive each other's services. Hence, denial of service. Another one is application denial of service. Here I have a picture of a website because applications and websites are technically the same thing. Applications are just more technical term for it. But application-specific denial of service is basically crashing the website itself, rendering the website itself unusable to the user. So even though the computers, the servers, and the electronics behind it are working perfectly fine, this attack just crashes the website itself, one specific website. And this is the type of denial of service that we are focusing on for this project specifically. So to understand how a denial of service attack is implemented, here I have a picture of a website. So when you look at a website is made out of codes, right? So this part of the website could be that code. That part of the website could be that code. Or that part of the website could be that code, right? Now, what hackers do is they probe these websites and figure out which part take the most resources. So say the search bar take the most resource here. What they would do is they would flood that with traffic until that part crashes. And if that part crashes, then the entire website crashes. This is our problem. Now we want to find a way to solve this. So here's how we plan to approach this problem. We need to do some testing, right? Because we're scientists, so we need to do testing. So we need a simple website, something like this. We need to be able to analyze how much each part of the website consumes in terms of resources, right? So new article could take that much resources, right here. Show could take that much resources, edit, and so forth and so forth. But instead, this is just like what a hacker would do, right? But instead of hacking the part that takes the most resources, we would write an algorithm. We would integrate that to our website, so that algorithm should be able to select the part that takes the most resources and just remove it automatically, while rendering the rest of the website still working perfectly fine. So then we should be able to do a second analysis of that website and show that the part that's taking the most resources is no longer taking any more resources. So we have a problem, now we have a proposed solution. Now it's time to actually code this and see if it actually works, right? So here's my part specifically for the summer, and actually this is the beginning part of the project. So I'll explain to you. My specific part for the project is to be able to put a website into a server so that we can access it with a computer and do some testing and all of that, right? Naturally, there's one criteria though that I need to fulfill that will contribute towards the success of the project, and that is speed. There are other criteria, but mainly it's speed. So speed, again, comes with its own challenges also. So here's the first one, flexibility. I know when you think about flexibility, you don't really think about speed, but in servers, it relates to speed, because space allocation, it takes time if you do it manually. You have to go around the lab if they're using the space, the servers in the memory. You don't want to do that. So yeah, you want to cut that on time, so you want to find a way to solve that. So flexibility is something that will contribute to our speed. Configuration also will contribute to our speed. We can't simply just upload the website into the server and expect it to work, right? The server has to be configured a certain way in order for the application to work a certain way. So configuration also will contribute to our speed. And then, of course, the automation. As you may know, generally computers can do things much faster than a human could. So doing all the things manually will take a lot longer than if we code something, a software that will do all of this automatically, right? So those are the challenges, and here's how we solve this for the summer. For the flexibility, we have moved the server into the cloud. What's great about the cloud is space allocation is easy. Launching a server is easy. We simply just have to code it. Just specify what we need out of the server, and then cloud will just give that to us. Same thing with Docker. We're using this tool called Docker that will allow us to specify what we need, how we want the application to be configured. Write that up. Say the application needs specific packages, needs certain files. We can just write that up in Docker, and Docker will download all of that for us and attach all of that for us. And then, of course, the actual software that I need to code that will combine the server, the cloud, the configuration, and do the uploads and all of that, and to get me my application. So here's the result of all of those hard work. We did just skip all of that, but here's the result of all of that hard work over the summer. For the cloud, I was able to code something that takes about 2 minutes and 49 seconds to launch. So this is good. However, it's at this stage that I realized that the configuration time depends entirely on the size of the application. It depends less on my coding ability. So I did not include it into my graph. However, we are working with the simple applications because we're simply trying to prove a concept here. So we expect the configuration to take about 1 minute and 5 minutes. As you can see here in my first attempt also, I was able to code something, an automation code that takes about 24 minutes and 2 seconds. It's good enough. So my entire first attempt launches an application in about less than 30 minutes, worst case scenario. However, there's one major downside in my first attempt, and that is it required an external process for it to work properly. So I knew then, my first attempt, that there's a lot of room to improve upon. So after some modification on my automation code and help from a mentor, I was able to polish that down into 2 minutes and 24 seconds. So, which is great. It's good enough for our purposes. That means we can launch an application in about less than 10 minutes and do some testing and all of that. So, however, I thought I could do even better than this. So after some researching the cloud and polishing the automation code even more, I was able to get the cloud down into 10 seconds and the automation code into 1 minute and 3 seconds. Perfect. That means worst case scenario, we can launch an application in about less than 7 minutes. So fantastic. And this is that in action. So here, as you can see, I know this doesn't look like typical software because it doesn't have that fancy graphical user interface that you guys are all used to. However, it is a software, and I'm pretty proud of it. So this is the, as you can see here, I typed in the test and then the name of my application, and it did all the OpenStack boot up and configured everything and uploaded everything to give me my sample application. Just to prove that this actually came from my software. As you can see here, I had specified the IP address and I'd access it through my browser, and that's my project. So that's my project. Now, you might say, launching an application, big deal, right? Anybody can do that. However, what I say to that is, what I say to that is that this thing is written in a way that it's stackable. On an application, because now we can stack tools on top of it, to get our data. So we can stack like New Relic on top of it, which is the tool that allows us to analyze the website to see how much resources it consumes. And then we can stack the algorithm on top of it pretty easily, integrate that easily to get our data. And then another thing that's great about this project, this thing that I built, is that since it's so fast, we can easily get multiple websites running in one day. So we can get lots of data in very short amount of time. And then another thing, there's just so many positives about my project, is that it's packageable. Right? The thing is, we can package it, and so we can say, oh, this application with specific features gets this data, and this package gets this data, and this package gets data. So it's organized, and we can see our data quickly, and we can see if our solution actually works perfectly. So after we get all of this done and actually get the data to prove it, to show that our concept works, then no more crashing a website with denial of service. So thank you guys so much for listening. I also want to take this time to thank the program, the INSET program. I've learned a lot. I cannot stress how much I appreciate what I've learned in span of weeks, not only in my chosen career field, but also general life skills that I will use for the rest of my life. So again, thank you guys for the entire team that makes this thing possible. Thank you, Luyan, Maria, Megan, and Dr. Nick, and Jens. I hope that you guys continue to provide these opportunity for more students in the future, because it's truly an amazing opportunity. So thank you guys again.